We have good news. We have very good news, in fact. Ta-da! It's a game! Oh boy! Oh boy, oh boy. Look at that. So, you'll notice the sky is not black anymore. It's a nice light blue, or baby blue, whatever you want to call it. I literally just changed the fill color from black to this, and so now it looks like a sky. There is no actual lighting, so none of these blocks are lit. You'll notice we have terrain generation now. It's nothing spectacular, but it's better than flat land. The world is still 1 block thick, and I can show you because we can mine blocks now. Look at that. We can just click them out of existence. Yeehaw! And you can also place blocks. So if I wanted to fix this, I could just do that. And it's not limited to places you've already removed blocks. You can place them literally anywhere you want. Right? You can just keep building up until you hit the max world height, and then you will no longer be able to build. Whee! If you fall through the world, you spawn in the sky above it. That's it. You can't die. So, yeah. So that's pretty much where we're at. I fixed the memory leak loading chunks, so we load all the chunks around us within render distance, which is fantastic. I can show you what happens if you increase the render distance. So if I go to like 8 chunks, it's going to cost quite a bit more graphics memory because it's not very optimized, but you can see the world loading. You can kind of get a good idea of it. Uh-oh, we might have just crashed. Failed to submit draw command. Uh-oh. Uh-oh. Let's try it this way. We'll go in. Wait, is that the right folder? That's not the right folder. I always get confused. It's in here, this one. Yes. Alright. So there we are. We have a larger world now. And it renders just fine. Now we load chunks asynchronously. So you can see them loading in as we move across the world. And we're still... Apparently we're having some sort of problem here. I don't know what that is, but I'll have to figure that out. It's not a memory leak. I know that. It's some sort of error because of the way that I fixed the memory leak. Quote, fixed. I didn't actually fix it. I just kind of fudged it. I'll show you. So over here in world.cpp, in this update function, I rearranged this from how it used to look. So we have a new variable called force vertex update. So this happens whenever you mine a block or whenever you remove one. We force a vertex update so that we make sure we have the correct vertex data being sent to the sorry, I'm getting a water. Being sent into the graphics pipeline. That way we can actually see our changes in real time. Excuse me. Okay, so the check happens down here, so that it's if we cross into a new if we cross from an old chunk into a new chunk, then we do this. Or if we're standing still and we've placed a block, we force a vertex update, we do this. And this just keeps the data up to date. I also changed around how these functions work, so they each lead into one another. So every frame we update, regardless of anything, we update the load list for the chunks. So we keep track of how many we've loaded, and then we set the bounds for how far out to render based on what chunk we're in. I'm so sorry, excuse me. Based on what chunk we're in, plus or minus the render distance. So the render distance gets passed to the world and stored in this variable right here. So in the constructor, it gets passed to the world, and same with the max chunks per frame for loading asynchronously, and a seed for the world. So I've set myself up to where we can save seeds at a later time, but we're not doing that currently. I should mention the world is currently different every time you run the game. because it creates a seed from whatever the current time is. So notice this is different from last time, and if I close it and run it again, it's different again. Completely different. And it will be different every time you run it. Yeah, so for each chunk that's around the player within render distance, regardless of if it's visible or not, we check if it's loaded. If it's not already loaded, if it is already loaded, then we don't need to load it again, right? That doesn't make sense. So if it's not loaded, check if there's one there that exists already. And if it doesn't exist in the load list, this is a function that checks whatever vector you pass in, so I can check if it's in like one of the other lists, right? So if it's not already in the load list, then put it in the load list. That's what it does. And then for each chunk in the load list, so we have to load up the load list, and then we have to iterate through the load list and do things with it, right? So after that, we will go through this loop as long as the number of chunks that we have loaded is less than the max number of chunks per frame. Less than or equal to the max chunks per frame. Max chunks per frame is the limit of how many chunks we're allowed to render every frame to maintain a constant frame rate. Or an acceptable frame rate. Otherwise, we'd be loading everything in here every frame, and that would be way too slow. Especially for really large render distances, like 16, 32, 64 chunks. So yeah, we get the chunk from the load list. We load the chunk, and we force a vertex update to make sure that we can see it. And we increase the number of chunks that we've loaded, and then we add it to the visible chunks list because it is potentially visible. We're not doing any frustum culling. I turned that off because it's broken. But we add it to the visible chunks list because it might be visible, because we know it's in render distance, and we know it is we know it's loaded now, right? So we know it's loaded, we know it's in render distance. We just don't know if it's in the frustum in front of the player. So remove the chunk from the load list since it's now loaded and we don't need to keep loading it, and then subtract one from the index to make sure everything still works out, because we've decreased the size of this container. And if we have hit the chunk loading limit per frame, stop looping because duh. And then after that, we update our information for the camera and the frustum, and then once again, if we move to a new chunk or we first forcing a vertex update, we go into here. So we set the new coordinates for the camera, and in the visible list, which was updated from the load list, see they all kind of lead into each other. The load list leads into the visible list, which leads into the render list, which leads into the unload list, right? They all kind of, it's like a linear pipeline kind of thing. So, in this, we get the chunk from the visible list, because it's populated already from load chunk. And we can guarantee that it's populated because this function always gets called before visible list, no matter what. Okay, now we get the chunk at that location, because this just stores a vector of x, z, it doesn't actually store a full chunk, so it's a little more memory efficient. This would check for frustum culling if it was defined, but it's currently not. So if I went up here and I went define frustum culling, it would change down. It would change down here like that. See, it would use this logic instead of just true, but it doesn't currently work. It's broken, and it runs fine without it. Now, so if true, it will always go in here. Checks if the chunk is loaded, which we know it is because it's in the. I don't know why that's. I really don't need that line, but if the chunk is loaded and it's not already in the renderable chunks list because we don't want duplicates, then put it in the renderable chunk list because it's able to be seen by the player if frustum culling was enabled. Put it in the chunk list if frustum culling is not enabled anyway, so that we have something to render and we don't crash by trying to allocate a buffer size of 0. And then remove it from the visible chunks list just to keep everything neat and tidy. Subtract 1 from the index since the container size of the vertex of the visible chunks list changed. Else, if the chunk is already in the renderable list, then remove it from the visible list because it shouldn't be here if it's already in the renderable chunk list. And then subtract 1 from the index. If the chunk is in the frustum but not yet loaded, do nothing. Wait for the chunk to be loaded in the next few frames. Just wait. Just don't do anything. If the chunk is not in the frustum at all, remove the chunk from the visible list because it's not visible to the player and should not be rendered. Here you go. I wonder why my cursor shows up as black in It's weird. In OBS, my cursor shows up as black, but on my screen it's white. That's interesting. Alright, and this was just debug information. Okay, so once we update the visible list, we go into the render list right here. So this is what actually gets passed into the vertex buffer for Vulkan. So for each chunk in the renderable chunks list, which is updated right here from the visible list, we get the chunk coordinates from within it, the renderable chunks list. And then we check if the distance to the chunk is greater than the render distance on either the X or Y, on either the X or Z axis, because the world is two-dimensional technically, and every chunk is the same height, so we don't have to account for that. And we're taking the absolute value because distance is always positive. So we just subtract our cam coordinates wherever our camera is, which is attached to the player. So wherever the player is, we subtract the chunk coordinates from that to give us the distance, and we do it for the Z-axis and the X-axis. And then we check if the X distance is greater than the render distance or the Z distance is greater than the render distance. That means it's too far away, so we put it in the unload list so it can be unloaded later. Then we remove the chunk from the renderable list so that it's no longer rendered. That's it. So this is like our render distance check again, but for the unload list, not the load list. Now, after the render list, we go into the unload list. And then for each chunk in that list, we just get the chunk coordinates from it. We get the... I'm sorry, I accidentally clicked the link. There we go. If the chunk is currently loaded and the distance to the chunk is greater than the render distance on either axis, which I don't know why that's there. I think that's just a mistake from copy and pasting. Sorry about that. So if the chunk is loaded, then unload it. That's it. And then remove it from this list and then subtract 1. That's it. Easy peasy. This is for getting block coordinates, getting chunk coordinates. This gets a block from the world, sets the block. We use this when we right-click to place a block. We use that. This gets a chunk from the chunk map. This gets another chunk from the chunk map, but using a vector 2xz as a position, so it's just an overload of the previous function. Load chunk. This will actually generate spheres of dirt, which is kind of cool. And that was just me testing to see if my generating was working correctly. But yeah, so here is terrain generation. It's literally just that. That's it. Let me do something kind of silly and I'll show you what this does, because I think it's cool. So if I play now, you're going to see that every chunk is a sphere. Every chunk is a sphere. Isn't that kind of weird? And it still works just fine too. It'll just load everything in just like normal. Pretty cool, huh? Now all of these are actually solid, so it does use quite a bit of memory, as you can see over here. But yeah. Anyway, let's move on. So terrain generation. Let's talk about that. So there's an object here called a terrain generator that I created. And in the terrain generator, it's a object here within the world, right? So within the world class, it's an object. Terrain generator, here it is. So we're using a library called libnoise. It's a very old library, and I had a lot of problems with it. It was kind of a struggle to get it set up. I ended up having to find some random guy's GitHub for it. Like he took the project and it had really old make files in it that don't work anymore, from like 2004, and so he reconfigured the project and set it up for like CMake, so you can just kind of build for whatever system you want. So if you want like a 64-bit version, you just build that. If you want a 32-bit version, you build that. If you want release or debug, you can build those too. If you want a DLL, a non-static library, then you can do that too. But I'm using static because it's easier. Now, so when the terrain generator gets created, it asks for a chunk width so that it knows how big the chunks are. That's important because we have this module that generates Perlin noise, and we have a noise map, which is actually our height map. It's not what we're actually going to use. We're going to use the image that we create from the height map in order to determine our terrain generation, right? And I'll show you that in a second. This is the builder that generates the height map. This will render it out into an image, and this will write it out to a file if you want to look at it. So the way this works is well, first of all, we're going to return an image pointer, which just points to this image. And the function is called getTerrain. You can see that. You're not blind. We take a chunk X coordinate and a chunk Z coordinate. So we just pass in whatever chunk we want to generate, and then we pass it a seed as well. The scalar is so that our world is either larger or like larger but less detailed, or smaller and more detailed. That's important because if I change this to some other value, we'll get like really crazy world generation. So if this is only just 1, it's going to look really weird. You'll see. I'll probably have to turn on flying too. Yeah, see? I mean, it works, but like everything is very compressed. Like these are all like mountains. They're just really compressed into smaller spaces, right? It works. And the reason it just looks weird is because since the world's only 1 block thick, it never generates anything below the block that it generates. Now, if I change it to something like 50, it gets really big. And then the world is too broad and the distances are too large. You'll see that here. We have the opposite problem, see, where the world's not detailed enough, right? It's very, very large distances. And so to kind of mitigate that, we pick the value that's 25, which is a little bit better, I think. You get a lot of features that aren't too small, but also aren't too big. And we're casting it to a double to make sure that it works properly within these functions. So this will pick the part of the terrain that we want to render. So this generates Perlin noise, right, from whatever you pass in. It's kind of hard to explain, but it's consistent coherent noise, right? So if you pass in like 0 0, you'll get an image, and then if you pass in 0 1, you'll get an image that's directly above that and will tile correctly with it. Does that make sense? Hopefully that makes sense. But it's coherent and it's tileable, and that's what these are for, right? So we need to pick what square of the world we want to generate, and then we pass that into this down here. So if the seed is -1, generate a new seed from the current time. That's what that does. The null has to be there for this to work. Apply the seed to the module, right? Then we're going to create the height map, so we need to set the source module for which module we're going to use to generate from. You can generate different modules. So instead of Perlin noise, you could use you could do a clamp, you could do constant, curve, cylinders. That's kind of cool looking. All kinds of these, module, multiply, powers. There's all these different ways to generate noise. So we set the destination noise map. That's going to be our height map up here, right? Noise map, height map. Our destination size is chunk width by chunk width, so we get a 16 by 16 image. So 1 pixel for each chunk, for each block, sorry. Then we set the bounds because that's the part of it we want to render, and then we build that height map. Right now, this generates a file. This generates a height map with coordinates from -1 to +1. So in order to get it from 0 to 255, which is what we need because that corresponds to the height of our chunk, we render it out to an image. So literally just, okay, here's the source height map, here's the image that I want you to put it in, render it. That's it. And then we normalize it to be within acceptable world coordinates. So this would put it from 0 to 255, but I don't want 255 to be, like, I don't want a mountain that goes all the way up to the max build height because you can't build on top of it. So a good range is, you know, like 0 to 127. That's half of the world height. So you can still build, you can build a whole mountain on top of another mountain if you want to, up to 255. And that's what this does. It just takes in each pixel of the image and then normalizes it. Rather than from 0 to 255, it'll go from 0 to 127, if that makes sense. And then it will return the image. And then optionally we can write it out to a BMP for debugging purposes, and I will show you what that looks like. It's going to write this file every frame, every time it loads a chunk, actually. So if you have an old hard drive, don't do this. Okay, so if we go into the CloneCraft folder, and it'll be in the project directory, I believe, terrain.bmp, here it is. If we edit, there it is, there's our terrain. It's very grayscale, but the values are different enough to where these aren't exactly the same color, and they're different enough to where you get a nice slopey looking terrain. So yeah, that's how that works. And I don't want to do that all the time, so I'm going to turn that off. So that's our terrain generator. It's very simple. It's only two-dimensional, so you can't have like a mountain that overhangs on other land because it's not three-dimensional. It's only two-dimensional. So you can't have things like that. What else? What else? So we talked about terrain generation. We talked about loading chunks, generating chunks. Excuse me. I might need to sneeze. I got the nose tickles. Oh god. Oh god. Okay, it went away. Okay, this is how we update the chunk. So I'll jump over to how my input works real quick, so I can show you left click, right click. Where is it? I'm sorry, I get lost. Okay, cool. Yeah, so down here we have a function that we declared called handle mouse button input. This is a callback for glfw. So when glfw is the thing I'm using to create the window, and I can interface with glfw to get messages from Windows. So like if I click, it'll call this function. glfw will call this function and do whatever it says, and that's passed in from main up here. So glfw set mouse button callback handle mouse button input. You pass it a function, and that's how that works. Same thing here. This is how we do keyboard input. This is how we do mouse input. I don't remember if I ever talked about those, but so we say, hey, if the left mouse button was pressed, then we have left clicked. That's it. And then if the right mouse button was released, then we have right clicked. That's how we know. We do release because I want it to happen on the release of the key, not on the press of the key. That way you can't just hold down the button and do it forever. Okay, and then so based on those controller button presses, right? And the controller is just a struct that has bools in it. It's very simple. Based on those inputs, we do things to the camera and the player, right? So if we press the speed modifier, that's when we press shift, we'll increase our speed, and I've wanted to increase that for a while, so I just did it. If we left clicked, we get the camera position, we create a ray. This is how we do this. I had to figure out ray casting. We pass it a position, which is the start and end in the beginning, and we pass it a direction. What direction is it going? It will always go directly straight out from the center of the camera. That's how you know what block you're pointing at. This will move the ray forward in a fixed step size. This is the end of the ray. This is the length of the ray. Very simple. So we create a ray, and for this ray, we pass it the camera position that we just came up here to start, that we came up with here to start with, and then we pass it the rotation of the player so that it's facing the correct way. It's facing the same way that the player is facing. Then we say if the length is less than or equal to the build range, which we set to 5, so you can build up to 5 blocks away from you, then we will do this, and then at the end of this we will iterate the ray one step forward by 0.05 units in the world. So then we cast the end of the ray. We see what point the end of the ray is currently at. Then we get the block at that position, right? And then we see, hey, is the block air? If it is, just keep circling. If it's not air, then we know we've hit a block in the world, and we want to set the block that we hit to air because we're mining, right? So we just set it to air. We don't actually delete anything. We're just setting the block ID to air. So we're just changing a digit, an 8-bit number. We're just changing that. So from whatever block it used to be, change it to air. But we don't want to collide with air, so we check to see if it's not air first. And then we update the chunk. Now here's where it gets interesting. So we update the chunk. We get the chunk position from the world vector. This is the chunk map. And then we regenerate its vertices and indices to make sure it's correct, and then we force a vertex update. This just well, first it clears its vertices and indices, and then it iterates through the chunk and generates vertexes and indexes from the block database according to the position of each block within the chunk. And then the coordinates for these blocks are in world coordinate format. They're not in chunk coordinate format, so that we don't have to convert them later when we put them in the vertex buffer. So that's how updating chunks works. And then that's for left click, and then the exact same thing happens for right click, except we set the block to grass instead of dirt. And we check the last ray position instead of using its current position. Because if we hit something, we want to put a block right before we hit that at whatever position is there, so that we can place it on whatever side of the block we're facing and make sure it gets placed in the right location. This does have some problems depending on how far your step is. So if you're like right on the corner of a block, sometimes you can put a block in the wrong position that you didn't mean to, but it's very finicky with that, so you have to be like really accurate if you want to mess it up like that. And that's pretty much that. There's a bunch of debug information that I'm not printing out. Oh, I changed the draw frame function a while back. I forgot to talk about it in the last video. But all of this stuff used to be static, and it was very difficult for me to figure out that I needed to recreate the buffer every frame and bind a new pipeline every frame. Right? So I had to reconstruct this and then figure all that out. And the way that this works is, well, we first wait for the previous, like if this fence is being used, it's like a mutex, right? So it's a way to synchronize. If it's being used, then we just wait for it so that we're not overwriting images that are already being rendered. This is the current image index. We get it from vk acquire next image khr. That's a Vulkan function. Then we update the uniform buffer to make sure all of our matrices are correct, our transformation matrices and our projection matrices. Oh god, it's been 30 minutes recording this. Jesus, I'm so sorry. I'll try to go fast. If it's out of date, then we recreate it. If the previous frame is using the image, wait for it. Mark the image as being used by this frame. Then do that. We start the command buffer because we're gonna put some commands in it for Vulkan to do. This is where we change our clear values. So this is the color of the sky right here. That's our color of the sky. This is a depth stencil for depth testing to make sure things render behind other things properly. And then this is render pass info. So this is like where you pass the clear values and stuff. I'm not going to go over that. This is beginning the render pass. Each render pass we will bind a pipeline for whatever command buffer we're currently on in the image index. So this is actually multi-threaded. This is our vertex buffer that we're passing in. You can pass in multiples if you want. I don't know how that works. I don't intend to find out. This is actually binding the vertex buffer. If this is 0, this will fail and the program will crash. That's why we have to make sure it's not 0. Same thing with the index buffer. This is the descriptor set that tells the program what my vertexes look like. This is the command that actually draws the frame using the indexes to index into the vertex buffer. Then we end the render pass, and then we close the command buffer because we're no longer recording to it. Then we need to submit the frame after it's done being rendered. So we create this structure here, which is just a bunch of information to tell it when to submit. So it's like, hey, we need to wait on these semaphores, these mutexes. We need to wait until the color attachment has finished outputting. So once the fragment shader is done and we have colors in the image, then you can present it. That's how we know it's done. And that's what these render finish semaphores are for. And it's for the current frame because we don't want to do it for another frame. That'd be really weird and cause a whole bunch of weird problems. Then we reset the fences because they're no longer being used, and then we can submit we can submit the graphics queue to the screen and actually present the image. That's what this is. So we present the image to the screen, and that's how we render. And this gets called every single frame, no matter what. So up here in the main loop, here it is, draw frame. So we update, which is this update function here. So we figure out where the player is, where the player is looking, all that stuff. Update the camera, update the player, update the world, check if we put any blocks down, and then we draw the frame. That happens every time. and it's very quick as you've seen. So yeah, we've gone over. We changed the world color. We changed around how chunks work. We changed around how we load things, how we pass them into the command buffer, how we're unloading things to maintain acceptable memory usage, and to make sure we don't have any memory leaks. We've figured out terrain generation, which wasn't all that difficult once I got the library actually working. So yeah, that's where we're at right now. What went right? Well, it was a pretty easy week actually, because I just kind of flew through it. I had done a whole lot of work last week and the week before to make sure that when I got to this stage, it would be just like a breeze, right? All I had to do was pass in a height value for the chunk when it's loaded, and that's it. That's how we did terrain generation. And then I also fixed collision detection, but that wasn't really that difficult. What else? Yeah, we can mine, and I figured out how to do ray casting in 3D. Wasn't too hard. That's pretty much it. Anything that went wrong this week? There wasn't really anything that went wrong other than trying to figure out how to use that libnoise library. This doesn't need to be here. Trying to figure out how to use this noise library was kind of weird. Just because I was having linker errors because the library is so old, but I figured that out, got it working. That's where we're at. We have a game. We can do things. We can build, and we can have fun. And yeah. Thanks for watching.